welcome to NPTEL course on power system protection. We are on module 4 on directional relaying, lecture 17 on superimposed component based directional relaying principle. Here we will see how we can exploit the memory polarization aspect, and then we will come to the memory superimposed component voltage and current, how they can be useful for directional relaying principle. Going further, let us first appreciate an issue. Now, suppose in a system we have already explained that a fault happens to be very close to the relay bus. In that case, all the voltages V A, V B, V C will collapse if the fault happens to be a voltage 3 phase fault. Once again, if the fault is close to the relay bus and happens to be a voltage 3 phase type, then all the voltages will collapse simultaneously. In that case, neither positive sequence nor negative sequence nor 0 sequence components will be available, nor the phase quantities also will be available. That means that the like you can see here, the voltages are as normal, fault happens to be there, all the 3 phase voltages collapse. This is a simulated data. However, if the corresponding system is a high voltage level, then as usual there will be capacitor voltage transformers, and the output of the capacitor voltage transformer for this step jump in voltage will be going through a subsidence transient, and their response will be like this. Note that this voltage should represent this voltage. So, this is also erroneous. So, with this kind of input, the relay, if it goes for the decisions, then that will be erroneous. So, all the techniques which we have till now narrated, they are clueless what to do. So, what we say that for closing faults such issues are there. So, in this case you can say that the solution is that the relay should use memory polarize the stored pre-fault data, pre-fault voltage to substitute the corresponding fault voltage there. In that case, that becomes good at. Like we know that the fault voltage phasor does not deviate much in terms of angular position with respect to the pre-fault voltage. So, considering that assumption, if you use the pre-fault voltage instead of the fault voltage in that situation, in such situations, then the relay can properly decide the directional relay. Because in directional relaying we saw that we have very large angle margin, and in that case the pre-fault voltage can be a good substitute, and in numerical relaying we have that scope, because the relay continuously stored data, and in case of an event which is to be recorded, the relay stores the data permanently. So, therefore, pre-fault voltage can be employed in such situation for correct directional relaying decision, and that is what we talk about memory polarization and so. In addition to that, because we are able to handle pre-fault voltages and currents in a numerical platform, the superimposed current called, which you consider separates the load flow current or the load current from the fault current, because we see that in case of positive sequence perspective, pre-fault current was affecting the performance of the relay. So, if you can subtract the pre-fault current from the fault component current, then that is called superimposed current. So, that has other advantage. Superimposed current and voltages can provide directional information, that we will see. So, before going to that perspective, let us first have clarity on the pre-fault, fault and so. This is the same system, 3-bus system, fault for this relay RM and forward fault, a 3-phase fault. So, normal current, 3-phase fault, all 3 phases current increase. This is the fault inception. So, from the fault inception 1 second, in this case simulated data, this is pre-fault, this is fault. So, we designate like this, before the fault is the pre-fault data and this is during the fault. So, this is fault data. Now, note that in the sequence component diagrams also we discuss also that if a fault happens to be there and the fault is associated with RF and so that the fault current flows like this. In addition to that, current also flow from left to right, that is the load current perspective. So, point is that the relay sees the current during fault, that is combination of both fault current, fault component of current and the load component of current. Now, in case of voltage also, let us, this is a single line to ground fault case, and you see that one of the phases having a substantially low voltage, other phases remain somewhat higher voltage than the normal voltage depending upon the system grounding and so. So, for this case fault inception at 1 second, this is the pre-fault voltage data, this is the fault, during fault the corresponding voltage data. So, in case of superpositions, both fault and pre-fault are being used. In case of memory polarizations, voltage you can say that pre-fault data, substitute the corresponding fault, you can say that during fault you can say that the corresponding data perspective. Now, let us, for a system 230 kV system, pre-fault current at one instant is 0.08 like this and the corresponding voltage is 135.0 and this. During fault the corresponding current is 0.41, 25 degree, 25.64 degree and V A is 12.7 with minus 87 DC. So, substantially lower voltage. So, now this is the pre-fault data set for that phase and this is fault data set for this case. So, we can, this voltage is substantially low means this voltage can substitute, this voltage can be substituted by this one. You see here the angle deviation between pre-fault voltage to fault is pretty low and that is what we are mentioning, that if you substitute with this in case of requirement, then the decisions on directional line can be still be good at. Now, we will go to how the superimposed component can be advantageous for directional principle. So, we will use Poitou sequence superimposed component, as already mentioned superimposed component, superimposed current is that the fault current minus the pre-fault current, that gives us, you can say that the corresponding superimposed component. Let us consider this system. So, we have fault at F1 for this relay forward fault. So, this is pre-fault sequence diagram, balance condition, Poitou sequence diagram only. This is the relay bus, pre-fault current through the relay observed by the relay, V1m pre-fault voltage relay Poitou sequence, I1m Poitou sequence current. Now, fault happens to be now at F1 forward fault. So, equivalent Poitou sequence diagram with ZF becomes like this. This we have already discussed in earlier lecture. So, ZF consists of the negative sequence and zero sequence if they are present and the corresponding 3 RF. So, series parallel combination of that gives you the equivalent ZF. During fault, we have this V1 MF and the corresponding I1M NMF relay current, so the fault component. So, we can write down for this circuit the V1M pre equals to EL, L bus voltage source equivalent source voltage, Thevenin's equivalent, minus I1M pre ZSL1 plus ZLM1, this impedance, source impedance plus this line impedance behind the relay. For fault condition, this voltage equals to EL minus this drop, with the current becomes the fault current through the relay I1 MN F. So, these are the two equations for this diagram. One is for pre-fault for this system and the other is for the fault. If you subtract this V1 MF, you get the subtraction of this V1 M pre from this V1 MF, then this side. So, equation, this equation minus this equation, that leads to minus 1 MF pre minus IMN1 pre MF minus pre fault current minus pre current, then the impedance behind the relay. So, then we get that suppose we define this corresponding this voltage difference to be delta V 1 m Poitiers sequence change in Poitiers sequence voltage, and this current change in current in the Poitiers sequence current seen by the relay, that we call the superimposed components. So, this delta V 1 m and delta I 1 m n Poitiers sequence voltage and Poitiers sequence current change defined as the superimposed components. So, this we designate with delta V 1 m and this we designate with delta I 1 m n, rest remaining same. Now, if you go to this delta V 1 m divided by delta I 1 m n, so that becomes negative. So, angle of this side equals to angle of this. So, therefore, if I designate this angle to be delta phi 1, so angle of delta V 1 m change in Poitiers sequence voltage observed at bus m by the relay minus change in Poitiers sequence current seen by the relay. This angle difference delta phi 1 equals to the angle of this negation of the angle of the impedance behind the relay. So, this impedance is always around 80 or above that. So, therefore, this is negative. So, that means that the corresponding delta phi 1 is negative for forward fault is in forward direction. So, similar to the earlier sequence component based, we have seen that in case of Poitiers sequence superimposed component delta V 1 and delta I 1, the angle difference gives us similar logic for the directional leading using superimposed component. Delta phi 1 is negative for forward fault. Now, another thing we see here, only difference is that we are not taking current angle minus voltage angle, we are taking now voltage angle minus current angle, that is the only difference. Now, going to the phasor diagrams like we did for the sequence component also. So, we have pre-fault and we have fault sequence diagram, Poitiers sequence diagram. Now, let us first go for the forward fault like what we have seen here. So, we have V 1 m pre, we have V 1 m fault. So, this is delta V 1. We have current lagging to this voltage I 1 m, I 1 f, we have I 1 pre. So, this is delta I 1. So, this delta I 1 we plot here at the origin and this delta V 1 we plot here at the origin. So, we see that the delta I 1 is leading to this delta V 1. So, our logic here is angle delta V 1 delta V 1 angle of delta V 1 minus angle of delta I 1. So, this becomes a negative. So, we say that the delta phi 1 is negative for this forward fault. Now, come to the reverse fault. So, current direction changes. Now, we see here same V 1 m pre, V 1 m f, delta V 1. Now, we see here I 1 m pre, I 1 m f, reverse fault. So, current is reverse. as compared to this. So, this is delta A 1, this is delta V 1. We plotted at the origin delta V 1 and delta A 1. You see here now the current is lagging, but we are taking the delta phi 1 angle of delta V 1 minus angle of I 1. So, again same conclusion, delta phi 1 is positive for reverse fault. So, this is what we say for forward fault delta phi 1 is negative, for reverse fault delta phi 1 is negative, similar to the sequence components or phase quantity based approach. So, applying this concept of superimposed components, we say that for the same 9 volt system, line to ground fault, same set of data I 1 this and the B 1 this is pre fault data, R 2 for R 2 I 1 is this, and from set of voltages V 1 is this. Note that this F 1 fault for both relays are forward fault. Now, fault data available, relay R 1 computed I 1, computed V 1, for R 2 computed this I 1 and computed the V 1 as we did for in earlier examples. Now, pre fault data sets, fault data sets. Note that we require now additional data sets, that is pre fault data. What is pre fault data? Just before the corresponding fault data, and note that the pre fault data, these are phasors. So, these phasors are computed using the pre fault waveform, current samples and voltage samples available either using DFT, cosine filters or least square and so. Now, we will employ the principles. So, for this case we will compare, first find out the delta I 1 will compute, delta I 1 is I 1 f minus I 1 pre and delta V 1 is V 1 f minus V 1 pre. So, for relay R 1 we have already computed this positive sequence currents and voltages. So, delta I 1 found out to be 0.19 angle minus 150.63 degree kilo ampere, delta V 1 is 51.51 angle 101.60 degree. So, compute the delta phi 1 using the relations delta V 1 minus delta I 1. Note that the change as I already mentioned. So, this is angle of voltage first, then the angle of current. So, this delta phi 1 for this case happens to be minus 107.77 degree. So, this how do you obtain this? If you see the, you can say that the delta V 1 is 101 minus 150. So, 101 plus 150 gives you, this is 251 degree. So, this 252 degree is greater than 180 degree. So, subtract 360 degree, then you got minus 107.7 degree, because already mentioned that these angles should be from the phasors, angle should be plus minus 180 degree. So, to get the corresponding angle proper one, we get the consider this. Otherwise, also with respect to the corresponding voltage, in this case the current leads. So, how much is the leading angle, that matters to us, and that leading angle is nothing but minus 107.77 degree. So, this is a case of minus angle means forward fault. So, which is being correctly identified by this superimposed quantity based directional line. Now, going to the R 2 side, the corresponding delta I 1 from this I 1 pre and the I 1 fault, delta V 1 from the V 1 fault and the V 1 pre happens to be like this. So, similar to this, employing this relation, we can find out delta phi 1 to be minus 104.93 degree, which is having negative angle, it implies forward fault, which is also correct. So, we see that for this case the superimposed component approach, both relays find the direction properly. For F 2 side, this is forward for R 2 and reverse for R 1. We have pre-fault data sets and we have fault data sets. Then compute the I 1 and V 1 for each set. For the fault data also like that, I 1 and V 1 and I 1 and V 1. Now, we will compute for this case for relay 1 using these relations delta I 1 and delta V 1. So, delta 1 is this and delta V 1 is this for relay R 1. So, also delta 1 and delta V 1 for relay R 2. Using the relations for edge angle, delta phi 1 equals to angle of delta V 1 minus angle of I 1, delta phi 1 equals to 75 degree, which happens to be positive, means this is reverse fault. So, for R 1 this is reverse fault, which is correct, and we say consider this is delta phi 1 equals to minus 104.404 degree. This for the also minus angle means forward fault. So, for R 2 this is forward fault, which is also correct. So, both relay R 1 find its relay R 1 finds it reverse fault and relay R 2 finds it forward fault, which is correct as we see from this simulation. With high fault resistance 120 ohm case, as we have seen earlier also, pre-fault data using we find the I 1 and V 1 for both the relays, fault data I 1 V 1 and I 1 V 1 for both the relays. This is the set of data available for the relay. Now, if you see this performance of the R 1, we got the delta phi 1 to be negative even though the fault resistance is very high, which is correct, and the delta phi 1 minus 114 degree is R 2, that is also correct. So, we see consider that both the relay correctly identify the direction of fault using the principle of superimposition quantities, and we see that the corresponding superimposed quantity also not affected by the fault resistance, and also this is not affected by the pre-fault current, because this is already subtracted from the fault quantity also. So, we say that the merits of superimposed components of directional link, that this is not affected by RF, not affected by the pre-fault as already mentioned. Being positive sequence based, this is available for all types, unlike negative sequence and zero sequence component. But the demerits is that because it uses the pre-fault component, the pre-fault samples are being projected to the fault side to find the corresponding delta A 1 and the delta V 1. If the frequency deviates during the fault, then the frequency accordingly the corresponding drift angle has to be compensated. These pre-fault require projections that has to be done correctly. Further, note that we have learned through these directional link principles using positive sequence, negative sequence, zero sequence and the superimposed component, positive sequence, negative sequence, zero sequence and this is superimposed component, positive sequence superimposed component delta phi 1. In all four angles we have the same logic. Negative angle means forward fault, positive angle means reverse fault. Also same thing logic we applied in case of the phase quantity also, whether it is 90 degree connections or normal phase quantities. So, in overall the sequence component and the superimposed components can complement each other. A good relay includes multiple principles to exploit more accurate and secure decisions, and that is what the modern relays are using today to obtain the proper direction of fault at numerous challenging conditions also. Thank you.